Have you ever looked up at the night sky and wondered why Saturn looks different from every other planet? Why it alone wears those magnificent ethereal rings like a cosmic crown? Tonight, we're going to uncover one of the solar system's most beautiful mysteries. And I promise you, the answer is far more dramatic and violent than you might imagine. If you find comfort in these gentle explorations of planetary science, I'd be grateful if you'd consider subscribing and liking this video. Maybe give it a few hype points if you feel like. The visuals are here for you, but feel free to close your eyes, let your mind drift, and imagine the cosmic ballet we're about to witness. Also, I'd love to know where you're watching from tonight. Comment your time and location below. Let's begin. Four and a half billion years ago, our solar system was nothing like the serene collection of worlds we see today. It was chaos, a violent nursery, where planets were still finding their places, where massive objects hurled through space at incomprehensible speeds, colliding and reshaping the very architecture of our cosmic neighborhood. And in this primordial violence, Saturn's rings were born. But here's what might surprise you. Those rings that make Saturn the jewel of our solar system, they're not ancient relics from the planet's formation. They're not permanent fixtures that have always been there. Instead, they're relatively young in cosmic terms. Perhaps only a few 100 million years old. That means Saturn's rings formed after complex life had already begun flourishing on Earth. The dinosaurs might have looked up at a ringless Saturn. This revelation challenges everything we thought we knew about planetary formation and forces us to ask an even deeper question. If Saturn's rings are young, what catastrophic event created them? And why is Saturn the only planet in our solar system to possess such a spectacular feature? The story begins with a fundamental misunderstanding that persisted for centuries. When Galileo first pointed his primitive telescope at Saturn in 1610, he saw something that baffled him completely. The planet appeared to have handles or ears, strange protrusions that he couldn't quite make sense of with his limited optics. He wrote in his notes that Saturn seemed to be triple, as if it were three separate worlds somehow connected. It wasn't until 1659 that Dutch astronomer Christian Huygens, armed with a better telescope, finally recognized what Galileo had glimpsed. Saturn was surrounded by a thin, flat ring that nowhere touched the planet. This discovery revolutionized our understanding of what planets could be, introducing the possibility that worlds could have features unlike anything we'd ever imagined. But even Huygens got it wrong. He thought Saturn had a single, solid ring, like a dinner plate surrounding the planet. It took another century and the keen observations of Giovanni Cassini to realize that what appeared to be one ring was actually multiple rings separated by gaps. The largest of these gaps, still called the Cassini division today, became the first clue that Saturn's ring system was far more complex and dynamic than anyone had dreamed. As telescopes improved and our observations became more detailed, the mystery only deepened. We discovered that Saturn's rings weren't solid at all, but composed of countless individual particles, each orbiting the planet independently. Some of these particles are as small as grains of sand, others as large as houses or even mountains. Together, they create the illusion of solid, continuous rings when viewed from a distance. But this raised an even more perplexing question. How do billions upon billions of individual particles maintain such perfect, organized rings? What forces keep them in such precise formation? The answer lies in one of the most elegant dances in our solar system, a gravitational choreography that involves not just Saturn, but its family of moons. Saturn's moons act like cosmic shepherds, their gravitational influence sculpting and maintaining the ring structure. Some moons orbit within the rings themselves, carving gaps as they sweep up material in their paths. Others orbit outside the rings, their gravitational pull preventing particles from spreading outward. Still others create resonances, invisible gravitational rhythms that organize particles into distinct bands and gaps. The moon Mimas, for instance, orbits Saturn exactly twice for every orbit of particles in the Cassini division. This 2-1 resonance creates a gravitational tug that pulls particles out of that region, maintaining the gap that Cassini first observed centuries ago. It's as if the moons are conductors, orchestrating a symphony of ice and rock that plays out over millions of years. But understanding how the rings maintain their structure is different from understanding how they formed in the first place. And this is where our story takes a darker, more violent turn. Because Saturn's rings tell a tale of destruction on a scale that's difficult to comprehend. The leading theory for ring formation involves what scientists call a disruption event. Imagine a moon or large asteroid, perhaps hundreds of kilometers across, wandering too close to Saturn. Every massive object has what's called a Roche limit, a boundary within which tidal forces become so strong that they overcome the gravitational forces holding an object together. Cross this invisible line, and the object begins to stretch, distort, and ultimately tear apart. Picture this doomed world approaching Saturn, its surface beginning to crack as the planet's immense gravity pulls harder on the side facing Saturn than on the side facing away. The difference might seem small, but across hundreds of kilometers, it becomes catastrophic. Mountains crumble, oceans boil away into space, and finally, the world itself comes apart in a cascade of destruction that scatters its remains across Saturn's equatorial plane. This isn't science fiction. We've observed similar disruption events in our own solar system. Comet Shoemaker-Levy 9 was torn apart by Jupiter's tidal forces in 1992, and we watched its fragments crash into the giant planet 2 years later. The same process that destroyed that comet could have created Saturn's rings, but on a much grander scale. Alternatively, the rings might have formed from a catastrophic collision between two of Saturn's moons. Imagine worlds hundreds of kilometers across smashing into each other at speeds of several kilometers per second. The impact would be so violent that both objects would be completely shattered, their remains spreading out into the orbital plane to form the rings we see today. Either scenario would have been a spectacular and terrifying event. If you could somehow have witnessed it from a safe distance, you would have seen Saturn's neighborhood transformed in a matter of hours or days. What had been empty space would suddenly be filled with a glittering debris field, countless fragments catching and reflecting sunlight as they settled into their eternal orbits. But here's what makes Saturn's rings truly unique. Other planets in our solar system have moons that occasionally wander too close or collide with each other. Jupiter, Uranus, and Neptune all have ring systems of their own, but they're faint, narrow, and composed of dark material. Why are Saturn's rings so dramatically different? The answer lies in a combination of factors that make Saturn special. First, Saturn's density is remarkably low, lower even than water. This means that despite its enormous size, its gravitational field has a particular structure that's ideal for maintaining stable ring systems. The Roche limit around Saturn extends much farther from the planet than around denser worlds, creating a larger zone where disruption events can occur. Second, Saturn's moon system is uniquely arranged. The planet has dozens of moons, many of them in orbits that intersect or come close to the ring region. This creates more opportunities for the gravitational interactions that both create and maintain ring structures. Saturn's moons also tend to be rich in water ice, which is highly reflective and creates the brilliant shining appearance that makes Saturn's rings so visually striking. Most importantly, Saturn sits in a region of the solar system where water ice remains stable. Closer to the Sun, ice sublimates away quickly, while farther out, organic compounds and other materials dominate. Saturn occupies a sweet spot where water ice particles can survive for hundreds of millions of years, maintaining their reflective properties and creating the spectacular light show we observe today. This is why Jupiter's rings are so faint. Despite being the largest planet in our solar system with the strongest gravitational field, Jupiter sits too close to the Sun. Any ice particles in its rings would quickly sublimate away, leaving behind only dark rocky material that barely reflects any light. The rings are there, but they're virtually invisible except in carefully processed photographs taken by spacecraft. Uranus and Neptune, on the other hand, are so far from the Sun that their ring particles are composed of organic compounds and other dark materials. These rings are narrow and faint, nothing like the broad, brilliant ring system that adorns Saturn. Only Saturn sits in the perfect location with the perfect combination of factors to create and maintain such a magnificent ring system. But there's another piece to this puzzle that makes Saturn's story even more remarkable. Recent observations have revealed that Saturn's rings are not just young in geological terms, they're actively changing before our eyes. The Cassini spacecraft, which studied Saturn for over 13 years before its mission ended in 2017, discovered that the rings are raining material down onto the planet's atmosphere at a rate that suggests they won't last forever. This ring rain, as scientists call it, consists of ice particles that become electrically charged and follow Saturn's magnetic field lines down into the planet's upper atmosphere. The rate of this precipitation suggests that Saturn's rings might disappear entirely within the next 100 million years, making them a temporary feature in the planet's long history. This discovery adds urgency to our quest to understand Saturn's rings. We're not just studying a stable, permanent feature of our solar system. We're witnessing a dynamic, evolving system that exists in a brief moment of cosmic time. In the grand sweep of planetary history, Saturn's rings are like a spectacular fireworks display, brilliant and beautiful, but destined to fade. The realization that we live during the precise moment in cosmic history when Saturn has rings is both humbling and extraordinary. Of all the billions of years that our solar system will exist, we happen to be here during the relatively brief period when Saturn wears its magnificent crown. It's as if the universe has given us front row seats to one of its most spectacular shows. But this raises yet another profound question. If Saturn's rings are temporary, could other planets develop ring systems in the future? Could Earth itself one day sport rings like Saturn? The answer is both fascinating and unsettling, involving processes that are still actively shaping our solar system today. Mars, for instance, has two small moons, Phobos and Deimos, both of which are slowly spiraling toward the planet due to tidal forces. Phobos, the larger and closer of the two, is expected to either crash into Mars or be torn apart by tidal forces within the next 50 million years. If it's disrupted rather than impacting the surface, Mars could develop a ring system, though it would be much fainter than Saturn's due to the composition of Phobos and Mars's distance from the Sun. Even more intriguingly, our own moon is slowly moving away from Earth due to tidal interactions, but this process will eventually reverse. In the far future, billions of years from now, the moon will begin spiraling back toward Earth. If it crosses Earth's Roche limit before impacting the surface, our planet could develop its own ring system. though this event is so far in the future that the Sun itself will have evolved into a red giant, fundamentally changing the nature of our solar system. These possibilities remind us that planetary systems are not static. They're dynamic, evolving entities where dramatic changes can occur over geological timescales. Saturn's rings are not just a beautiful feature of our current solar system. They're a window into the ongoing processes that continually reshape the worlds around us. The violence that created Saturn's rings wasn't a single, isolated event, but part of a much larger story of planetary evolution that continues to this day. As we peer deeper into the mechanics of ring formation, we discover that Saturn's neighborhood has been shaped by a series of catastrophic encounters that would make the most dramatic science fiction pale in comparison. Consider what happens when a moon approaches Saturn's Roche limit. The process doesn't begin with sudden destruction, but with a slow, inexorable stretching that could last thousands of years. As the doomed world draws closer to Saturn's gravity, the planet begins to deform it, pulling it into an elongated shape like a cosmic egg. Tidal forces work relentlessly, heating the interior through constant flexing and stretching until volcanic activity erupts across the surface. But this is just the prelude to destruction. As the moon crosses the Roche limit, the tidal forces finally overcome the world's own gravity. What happens next depends on the internal structure of the victim. A solid, rocky body might crack along fault lines, breaking apart in massive chunks that retain some structural integrity. But a loosely bound collection of ice and rock, held together by weak gravitational forces, would simply come apart like a sandcastle in a hurricane. The debris doesn't immediately form the organized rings we see today. Initially, the destruction creates a chaotic cloud of material orbiting Saturn at various distances and angles. Some fragments are flung outward by the violence of the breakup, escaping Saturn's gravitational influence entirely. Others crash into the planet's atmosphere in a spectacular meteor shower that would have illuminated Saturn's skies for decades. But the majority of the material settles into the equatorial plane, where the complex dance of orbital mechanics begins to organize the chaos into the structured rings we observe. This process takes millions of years, as gravitational interactions between particles and Saturn's moons slowly shepherd the debris into distinct bands and gaps. The sheer scale of this destruction is difficult to comprehend. The amount of material in Saturn's rings suggests that the original disrupted object was substantial, perhaps the size of one of Saturn's current mid-sized moons, like Enceladus or Mimas. Imagine an entire world, complete with its own geology, potential subsurface oceans, and perhaps even primitive forms of life, reduced to countless billions of orbiting fragments in a matter of hours. This raises profound questions about the nature of destruction and creation in our solar system. The same violent processes that destroyed a world also created one of the most beautiful sights in our cosmic neighborhood. Saturn's rings are simultaneously a monument to destruction and a testament to the universe's ability to create order from chaos. But the story becomes even more intriguing when we examine the composition of the ring particles themselves. The Cassini spacecraft's detailed analysis revealed that Saturn's rings are composed almost entirely of water ice, with only trace amounts of rocky material. This composition tells us something crucial about the object that was destroyed to create them. Pure water ice suggests that the original body was either a comet-like object rich in volatiles, or a moon that had been processed by Saturn's gravitational forces over millions of years. If it was a moon, the tidal heating from Saturn's gravity would have driven off lighter elements and left behind a core rich in water ice. This process, called differentiation, is still occurring today in some of Saturn's moons, particularly Enceladus, which vents water vapor and ice particles into space through geysers at its south pole. The purity of the ring material also explains their remarkable brightness. Water ice is one of the most reflective substances in the solar system, capable of reflecting up to 90% of the sunlight that hits it. This is why Saturn's rings shine so brilliantly against the black backdrop of space, creating the ethereal appearance that has captivated observers for centuries. But this brightness comes with a cost. The same processes that make the rings beautiful are slowly destroying them. Solar radiation breaks down the ice particles over time, creating charged particles that interact with Saturn's magnetic field. These charged particles spiral along magnetic field lines and rain down into Saturn's atmosphere, gradually depleting the ring system. The Cassini mission revealed that this ring rain is happening much faster than scientists had previously thought. The spacecraft detected a constant shower of charged particles flowing from the rings into Saturn's upper atmosphere, particularly in the region between the planet and its innermost ring. This discovery revolutionized our understanding of ring dynamics and suggested that Saturn's rings are much younger than previously believed. If the rings were ancient, billions of years old, they would have been completely depleted by this process long ago. The fact that they still exist in their current magnificent form suggests they formed relatively recently in cosmic terms, perhaps only a few 100 million years ago. This means that Saturn's rings are younger than complex life on Earth, younger than trees, younger than fish swimming in ancient oceans. This youth has profound implications for our understanding of planetary system evolution. It suggests that catastrophic events capable of creating ring systems are not just relics of the chaotic early solar system, but ongoing processes that can reshape planetary neighborhoods even in relatively recent times. Saturn's rings are evidence that our solar system remains a dynamic, evolving environment where dramatic changes can occur on timescales that are brief in cosmic terms, but vast in human experience. The discovery of ring rain also provides us with a natural laboratory for studying the interaction between planetary magnetospheres and orbiting debris. As charged particles from the rings flow along Saturn's magnetic field lines, they create complex electrical currents and plasma interactions that we're only beginning to understand. These processes offer insights into similar phenomena occurring around other planets, and even in exotic environments like the magnetospheres of neutron stars. But perhaps the most remarkable aspect of Saturn's ring rain is what it tells us about the planet's atmosphere. The constant influx of water from the rings is actually changing Saturn's atmospheric composition, adding hydrogen and oxygen that alter the planet's chemistry and potentially its weather patterns. Saturn is literally consuming its own rings, incorporating them into its atmospheric system in a process that connects the planet's interior dynamics with the orbital mechanics of its ring system. This consumption process raises tantalizing questions about Saturn's past. If the current rings are young and temporary, could Saturn have had other ring systems in its history? Could the planet have worn different crowns at different times, each created by separate catastrophic events, and each eventually consumed by the planet itself? The evidence suggests this might be the case, implying that Saturn has been through multiple cycles of ring creation and destruction over its 4.5 billion year history. The gravitational interactions that maintain Saturn's current ring structure are incredibly complex, involving not just the planet and its major moons, but also countless small moonlets embedded within the rings themselves. These moonlets, some only a few kilometers across, act as gravitational anchors that create gaps, waves, and spiral patterns in the surrounding ring material. They're like cosmic sculptors, constantly reshaping their environment through their gravitational influence. Some of these moonlets are visible as bright dots moving through the rings, while others reveal themselves only through the patterns they create in the surrounding particles. The Cassini spacecraft discovered dozens of these tiny worlds, each one a unique laboratory for studying gravitational dynamics in action. Some create propeller-shaped disturbances in the ring material, while others generate spiral waves that propagate outward like ripples on a pond. The discovery of these moonlets has revealed that Saturn's rings are far more active and dynamic than anyone had imagined. Rather than being a static collection of orbiting debris, the rings are constantly changing, with new structures forming and evolving on timescales of years or decades. Material clumps together to form temporary moonlets that may last for centuries before being disrupted and scattered. Gaps open and close as gravitational resonances shift. Spiral waves propagate through the ring material, carrying energy and angular momentum from one region to another. This dynamic behavior suggests that Saturn's rings exist in a delicate balance between the forces trying to spread them out and the forces trying to confine them. Saturn's gravity wants to pull all the ring material down to the planet's surface, while the centrifugal force of orbital motion pushes it outward. The moons provide additional gravitational shepherding, preventing the rings from either collapsing inward or spreading outward beyond their current boundaries. But this balance is temporary. The ring rain process is slowly winning, depleting the ring system and transferring its material to Saturn's atmosphere. In cosmic terms, we're witnessing the final act of a spectacular drama that began with the violent destruction of a world and will end with the complete incorporation of its remains into Saturn's atmospheric system. This inevitable fate adds a sense of cosmic urgency to our appreciation of Saturn's rings. We are living during a precious window of time when one of the solar system's most spectacular features exists in its full glory. Future generations of humans, if they venture to Saturn's neighborhood, will see a very different sight. The brilliant rings that have inspired poets and scientists for centuries will have wisps, and faded to thind eventually, they will vanish entirely. But the story of Saturn's rings becomes even more extraordinary when we consider the precise timing of their observation by human civilization. For most of Earth's history, no conscious observers existed to witness Saturn's celestial crown. The rings could have formed and disappeared millions of times throughout Earth's past without any awareness of their existence. Yet they happened to form and persist during the exact cosmic moment when intelligent life emerged on a small rocky planet that could appreciate their beauty. This cosmic coincidence raises profound questions about observation and meaning in the universe. Are we simply fortunate to exist during this brief moment when Saturn displays its rings? Or does our presence as observers somehow play a role in the story itself? While science cannot answer such philosophical questions definitively, the timing remains one of the most remarkable aspects of Saturn's ring system. The uniqueness of Saturn's rings becomes even more apparent when we examine the failed attempts of other planets to maintain similar systems. Jupiter, despite being the largest planet in our solar system with the strongest gravitational field, has only managed to maintain thin, dark rings composed of dust particles blasted off its inner moons by micrometeorite impacts. These rings are so faint they were only discovered when the Voyager spacecraft passed by Jupiter in 1979, and even then, they were visible only when backlit by the sun. Jupiter's ring system tells a story of constant renewal rather than catastrophic formation. Unlike Saturn's rings, which formed from a single massive disruption event, Jupiter's rings are continuously replenished by dust kicked up from its small inner moons. This dust quickly spirals into Jupiter's atmosphere, creating a ring system that exists in a steady state of creation and destruction. The particles never have time to organize into the spectacular structures we see around. They're consumed by the planet almost Saturn, because as quickly as they're created. Uranus presents yet another variation on the ring theme. This tilted world, spinning on its side due to some ancient collision, possesses narrow rings that are among the darkest objects in the solar system. Composed of organic compounds and rocky material, these rings absorb more than 90% of the light that hits them, making them nearly invisible except under specific observational conditions. They were discovered only in 1977, when astronomers noticed stars blinking on and off as Uranus passed in front of them during an occultation. The darkness of Uranus's rings reflects the planet's distance from the Sun and the different materials available in the outer solar system. At Uranus's distance, water ice becomes less stable, and organic compounds dominate the composition of small bodies. The result is a ring system that exists more as a theoretical curiosity than a visual spectacle, visible only to our most sophisticated instruments. Neptune's rings are perhaps the most mysterious of all. Discovered by Voyager 2 in 1989, they appear as incomplete arcs rather than continuous circles, concentrated in bright segments with names like liberty, equality, and fraternity. The gravitational mechanisms that maintain these arc-like structures are still not fully understood, involving complex interactions with Neptune's moon Triton and other factors that create asymmetries in what should be circular ring systems. Each of these planetary ring systems tells its own story of formation and evolution, but none match the grandeur and complexity of Saturn's rings. This isn't merely a matter of scale or brightness, though Saturn's rings certainly excel in both categories. It's a fundamental difference in the processes that created and maintain these systems. Saturn's rings represent the outcome of a perfect storm of circumstances that may be unique in our solar system. The gravitational resonances that organize Saturn's rings into distinct bands and gaps are particularly remarkable examples of celestial mechanics at work. These resonances occur when the orbital period of ring particles matches simple ratios with the orbital periods of Saturn's moons. A particle orbiting at a distance where it completes exactly 2 orbits for every 1 orbit of the moon Mimas, for example, experiences regular gravitational tugs that either clear material from that region or concentrate it there. These resonant relationships create patterns that extend throughout Saturn's ring system. The Cassini division, that prominent gap first observed centuries ago, exists because particles orbiting there are in a 2.1 resonance with Mimas. Every second orbit, they receive a gravitational nudge from the moon that eventually pushes them out of that region entirely. Similar resonances with other moons create dozens of smaller gaps and divisions throughout the ring system. But resonances don't just create gaps. They also create some of the most beautiful structures in Saturn's rings. Spiral density waves, first predicted by theoretical calculations and later observed by the Cassini spacecraft, propagate outward from resonance locations like cosmic tsunamis. These waves compress and rarefy the ring material as they pass, creating alternating bands of higher and lower particle density that spiral outward from their source. The mathematics describing these spiral waves are identical to those used to understand the spiral arms of galaxies, revealing deep connections between phenomena occurring on vastly different scales. Just as gravitational perturbations from massive objects create spiral structures in galactic disks, the gravitational influence of Saturn's moons creates spiral patterns in the planet's rings. The same fundamental physics operates whether we're studying a ring system spanning hundreds of thousands of kilometers, or a galaxy spanning hundreds of thousands of light years. These wave phenomena demonstrate that Saturn's rings are not merely collections of orbiting debris, but complex dynamical systems governed by the same mathematical principles that describe fluid dynamics, plasma physics, and wave propagation. The rings behave more like a fluid than a collection of solid particles, with waves, turbulence, and other fluid-like behaviors emerging from the collective motion of billions of individual components. This fluid-like behavior has allowed scientists to use Saturn's rings as a laboratory for testing theories about disk dynamics that apply to many other astrophysical systems. The formation of planetary systems from protoplanetary disks, the evolution of galaxy structures, and even the behavior of matter around black holes all involve similar physical processes. By studying Saturn's rings in detail, we gain insights into phenomena occurring throughout the universe. The Cassini spacecraft's 13-year mission revolutionized our understanding of these ring dynamics by providing unprecedented detail about structures that had previously been glimpsed only as fuzzy features in ground-based telescopes. The spacecraft revealed that what appeared to be smooth, continuous rings were actually composed of countless individual ringlets, each with its own distinct characteristics and evolutionary history. Some of these ringlets show signs of being disrupted and reformed multiple times, suggesting that Saturn's rings are constantly recycling their material through processes of aggregation and disruption. Particles clump together under their mutual gravitational attraction, forming temporary moonlets that may survive for years or centuries before being torn apart by tidal forces or collisions with other objects. The debris from these disruptions then becomes available to form new structures, creating a continuous cycle of creation and destruction within the ring system. This recycling process helps explain how Saturn's rings maintain their sharp edges and distinct divisions, despite the natural tendency of orbital mechanics to spread material outward over time. Without some mechanism to constantly reshape and reorganize the ring material, the sharp boundaries we observe would blur and fade within a few million years. The ongoing cycle of aggregation and disruption provides this mechanism, continuously refreshing the ring structure and maintaining its spectacular appearance. The discovery of these dynamic processes has also revealed that Saturn's rings are much more massive than previously thought. Early estimates based on their brightness suggested they contained only about as much material as a small moon a few hundred kilometers across. But detailed analysis of gravitational effects on the Cassini spacecraft during its final orbits revealed that the rings are significantly more massive, containing perhaps twice as much material as originally estimated. This additional mass has important implications for understanding both the rings' formation and their future evolution. A more massive ring system would have formed from the disruption of a larger original body, perhaps a moon comparable in size to one of Saturn's current major satellites. It would also take longer to be depleted by the ring rain process, extending the lifetime of Saturn's spectacular crown. The increased mass estimate also affects our understanding of the ring's age. While they're still considered young in geological terms, the larger amount of material means they could potentially survive for several 100 million years rather than the 100 million years suggested by earlier calculations. This extended lifetime increases the probability that intelligent observers would exist during the ring's spectacular phase, making our cosmic timing somewhat less miraculous, but no less remarkable. But perhaps the most intriguing implication of the ring's greater mass is what it suggests about the violence of their formation. The disruption of a moon several hundred kilometers across would have been a catastrophic event of almost unimaginable proportions. The energy released would have exceeded that of the largest volcanic eruptions in Earth's history by many orders of magnitude. The process would have heated the debris to thousands of degrees, vaporizing volatile materials and creating a glowing cloud of plasma that would have been visible from interplanetary distances. As this superheated debris cooled and condensed, it would have formed the countless ice particles that make up Saturn's rings today. The cooling process would have taken thousands of years, during which Saturn would have been surrounded by a glowing nebula of vaporized rock and ice, gradually condensing into solid particles. Any hypothetical observers in Saturn's neighborhood would have witnessed one of the most spectacular light shows in solar system history. The aftermath of this catastrophic event would have fundamentally altered Saturn's entire moon system. The gravitational perturbations from the disruption would have affected the orbits of Saturn's other moons, potentially triggering additional collisions or ejecting some satellites from the system entirely. The debris cloud itself would have posed a hazard to any surviving moons, sandblasting their surfaces with high-velocity particles and potentially stripping away atmos of materials. Everneres or surface today, billions of years later, we can still see evidence of this ancient violence in the detailed structure of Saturn's rings. Certain features, particularly in the outer regions, show asymmetries and irregularities that may preserve traces of the original disruption event. These fossil structures are gradually being erased by the ongoing dynamical evolution of the ring system, but they provide tantalizing clues about the catastrophic birth of Saturn's crown. The realization that we can read the history of ancient catastrophes in the current structure of Saturn's rings opens up new possibilities for understanding the evolution of our entire solar system. Similar disruption events may have occurred around other planets throughout solar system history, leaving behind traces that we're only beginning to learn how to recognize and interpret. This forensic approach to planetary science, reading the stories of ancient violence preserved in current observations, represents a new frontier in our understanding of how planetary systems evolve. Saturn's rings are not just a beautiful feature of our current solar system, but a library containing information about processes that shape the architecture of planetary systems throughout the universe. As we continue to decode this celestial library, we're developing new appreciation for the dynamic nature of planetary systems and the role that catastrophic events play in their evolution. The violence that created Saturn's rings was not an isolated incident, but part of a larger pattern of planetary evolution that continues to shape worlds throughout the cosmos. This understanding transforms our perception of Saturn from a serene gas giant adorned with elegant rings into a world shaped by cosmic violence and ongoing dynamical processes. The rings themselves become not just objects of beauty, but windows into the fundamental processes that govern planetary system evolution throughout the universe. The story of Saturn's rings is ultimately a story about the power of gravity to both create and destroy, to shape matter on scales ranging from individual particles to entire planetary systems. It's a reminder that the universe operates according to physical laws that can produce both breathtaking beauty and devastating violence, often as part of the same process. In Saturn's rings, we see the universe's capacity for transformation, its ability to create order from chaos and beauty from destruction. We witness the interplay between construction and destruction that drives cosmic evolution, creating temporary structures of magnificent complexity before ultimately recycling their material into new forms. This cosmic recycling process connects Saturn's rings to the broader story of stellar and planetary evolution, reminding us that all matter in the universe is constantly being transformed from one form to another. The ice particles in Saturn's rings will eventually be consumed by the planet's atmosphere, but the atoms they contain will continue their cosmic journey, perhaps someday becoming part of new worlds orbiting distant stars. As we stand on the threshold of a new age of space exploration, with missions planned to study Saturn and its rings in even greater detail, we're poised to uncover new chapters in this remarkable story. Future spacecraft may witness the ongoing evolution of ring structures, observe the formation of new moonlets, or even detect the subtle changes that herald the eventual fading of Saturn's magnificent crown. But regardless of what future observations reveal, Saturn's rings will remain one of the most remarkable features of our solar system, a testament to the universe's capacity for creating beauty through violence and order through chaos. They remind us that we live in a dynamic cosmos where spectacular changes can occur on timescales both vast and brief, where the same physical processes that can destroy entire worlds can also create some of the most beautiful sights in the universe. The rings we observe today are not static monuments to that ancient destruction, but living, breathing systems that continue to evolve with each passing moment. The Cassini spacecraft revealed that Saturn's rings pulse and ripple like a vast cosmic ocean, responding to gravitational tides from the planet's many moons with a grace that seems almost organic in nature. Consider the intricate dance of particles within what we call the spokes, those mysterious radial features that appear and disappear in Saturn's rings like ghostly fingers reaching across the ring plane. These ethereal structures, first glimpsed by Voyager and studied in detail by Cassini, form when tiny ice particles become electrically charged and rise above the ring plane, defying the gravitational forces that normally keep them confined to their orbital paths. The spokes appear most prominently during Saturn's equinox periods, when the sun shines edge-on through the rings, creating dramatic shadows that reveal the three-dimensional structure of these otherwise flat disks. During these rare alignments, which occur only once every 15 Earth years, the rings transform into a landscape of towering mountains and deep valleys, casting shadows hundreds of kilometers long across the ring plane. These shadow-casting features tell us that Saturn's rings are not the perfectly flat structures they appear to be from a distance. Instead, they possess a complex vertical architecture with clumps of material rising several kilometers above and below the main ring plane. Some of these vertical structures are permanent features maintained by gravitational resonances with Saturn's moons, while others are temporary formations that appear and disappear over periods of days or weeks. The discovery of this vertical structure revolutionized our understanding of ring dynamics and revealed new mechanisms by which ring particles interact with each other and with Saturn's magnetic field. The charged particles that create the spokes follow complex trajectories that depend not only on Saturn's gravity, but also on electromagnetic forces that can lift them above the ring plane and cause them to drift in directions that seem to violate the simple rules of orbital mechanics. This electromagnetic component of ring dynamics connects Saturn's rings to the planet's magnetosphere, that invisible bubble of magnetic field lines that surrounds Saturn and extends far into space. The magnetosphere traps charged particles from the solar wind and accelerates them to high energies, creating radiation belts that pose hazards to spacecraft and influence the behavior of ring particles. The interaction between Saturn's rings and its magnetosphere creates a feedback loop that affects both systems. The rings act as a source of material for the magnetosphere, contributing water vapor and charged particles that alter the properties of Saturn's radiation environment. At the same time, the magnetosphere influences ring dynamics through electromagnetic forces that can sculpt particle distributions and create the mysterious spoke features. This coupling between rings and magnetosphere represents a type of planetary system we've never encountered elsewhere in our solar system. While other planets have magnetospheres and some have rings, only Saturn possesses both in such spectacular abundance, creating opportunities for interactions that don't exist around any other world we've studied. The uniqueness of this system becomes even more apparent when we consider the role of Saturn's largest moon, Titan, in shaping the planet's entire neighborhood. Titan, larger than the planet Mercury and shrouded in a thick, orange atmosphere, orbits Saturn at a distance that places it well outside the ring system, but within the planet's magnetosphere. This massive moon acts as a gravitational anchor that helps stabilize the orbits of Saturn's other satellites and may play a crucial role in preventing ring material from spreading too far outward. Titan's thick atmosphere, composed primarily of nitrogen with traces of methane and other hydrocarbons, interacts with Saturn's magnetosphere in complex ways that we're still trying to understand. The moon's atmosphere extends far into space, creating a kind of atmospheric tail that stretches behind Titan as it orbits Saturn. This tail interacts with ring particles and other moons, potentially influencing their orbits and contributing to the overall stability of Saturn's system. But Titan's influence extends beyond gravitational and atmospheric effects. The moon's surface, hidden beneath its opaque atmosphere, harbors lakes and seas of liquid methane and ethane, creating a hydrological cycle unlike anything else in our solar system. These hydrocarbon lakes undergo seasonal changes as Titan orbits Saturn, with some regions experiencing methane rainfall, while others endure long dry periods. The methane cycle on Titan provides a fascinating parallel to the water cycle on Earth, but operating at temperatures so cold that methane, which exists as a gas in Earth's atmosphere, becomes a liquid that can form rivers, lakes, and clouds. This alien hydrological system represents one of the most active geological processes in the outer solar system, constantly reshaping Titan's surface through erosion, deposition, and seasonal changes. The existence of liquid hydrocarbons on Titan's surface raises intriguing questions about the potential for exotic forms of life that might operate using completely different chemistry than Earth-based organisms. While such life remains purely speculative, Titan's complex chemistry and active geology make it one of the most promising targets for astrobiological investigation in our solar system. The relationship between Titan and Saturn's rings becomes even more intriguing when we consider the long-term evolution of the system. Titan is gradually spiraling outward from Saturn due to tidal interactions, just as our moon is slowly moving away from Earth. This outward migration affects the gravitational balance that helps maintain Saturn's ring system, suggesting that the ring's ultimate fate may be tied to Titan's orbital evolution. As Titan moves farther from Saturn over millions of years, its gravitational influence on the ring system will weaken, potentially allowing ring material to spread outward or collapse inward more rapidly than it does today. This creates another constraint on the lifetime of Saturn's rings, independent of the ring-rain process that is currently depleting them. The complex web of gravitational relationships between Saturn, its rings, and its moons creates a system so delicately balanced that small changes can have profound consequences. The addition or removal of a single large moon could dramatically alter the structure and stability of the entire ring system, while changes in the rings themselves could affect the orbits and evolution of Saturn's satellites. This interconnectedness extends to the smaller scales within the ring system itself. Individual ring particles don't orbit Saturn in isolation, but constantly interact with their neighbors through gentle collisions, electromagnetic forces, and mutual gravitational attraction. These microscopic interactions, when multiplied across billions of particles, create the macroscopic structures and behaviors we observe in the rings as a whole. The collisional dynamics of ring particles represent one of the most complex many-body problems in physics, involving interactions between countless objects under the influence of multiple gravitational and electromagnetic forces. Computer simulations of these interactions require some of the most powerful supercomputers available, and even then can only model small portions of the ring system for limited periods of time. Despite these computational challenges, numerical simulations have revealed remarkable insights into ring behavior and evolution. They've shown how particles can spontaneously organize themselves into spiral waves and density patterns, how temporary moonlets can form and dissolve, and how the ring system as a whole responds to perturbations from Saturn's moons. These simulations have also revealed that Saturn's rings exist in a state of constant flux, with material constantly moving between different regions and structures forming and dissolving on timescales ranging from hours to centuries. What appears to be a stable, unchanging system is actually a dynamic environment where particles are constantly rearranging themselves in response to the complex forces acting upon them. The realization that Saturn's rings are dynamic systems has important implications for understanding their formation and evolution. Rather than being the direct result of a single catastrophic event, the rings we see today may represent the cumulative outcome of many smaller disruption events, collisions and capture processes that have occurred over hundreds of millions of years. This more complex formation scenario could explain some of the puzzling features of Saturn's rings, such as the presence of material with different compositions in different regions, and the existence of structures that seem too organized to have formed from a single chaotic disruption event. It also suggests that Saturn's rings may have gone through multiple phases of evolution, with periods of growth alternating with periods of depletion. The possibility of multiple formation events raises intriguing questions about the history of Saturn's neighborhood and the frequency of catastrophic encounters in the outer solar system. If Saturn has experienced several ring-forming events throughout its history, similar processes may have affected other planets as well, creating temporary ring systems that formed and disappeared long before human observers existed to witness them. This perspective transforms our understanding of planetary system evolution from a process that occurred primarily during the early, chaotic phase of solar system formation to an ongoing phenomenon that continues to reshape planetary neighborhoods throughout cosmic history. Saturn's rings become not just a unique feature of our current solar system, but evidence of processes that may be operating around planets throughout the galaxy. The study of Saturn's rings has thus evolved from a purely descriptive endeavor focused on cataloging their features to a comprehensive investigation of fundamental physical processes that operate throughout the universe. The rings serve as a natural laboratory where we can study gravitational dynamics, electromagnetic interactions, collisional processes, and fluid mechanics under conditions that cannot be replicated on Earth or in laboratory experiments. This laboratory aspect of Saturn's rings has made them invaluable for testing theoretical models and numerical simulations that apply to many other astrophysical systems. The same mathematical frameworks used to understand ring dynamics also describe the behavior of protoplanetary disks around young stars, the accretion disks around black holes, and the spiral structure of galaxies. By studying Saturn's rings in detail, we gain insights into these other systems that would be impossible to obtain through direct observation. The rings provide a nearby, well-resolved example of disk dynamics that we can study with spacecraft missions, ground-based telescopes, and theoretical models, creating a comprehensive understanding that informs our interpretation of similar phenomena throughout the universe. The success of this approach has inspired efforts to find and study ring systems around other planets beyond our solar system. While we haven't yet detected rings around extrasolar planets directly, theoretical models suggest that such systems should be common around giant planets in other stellar systems. The techniques developed for studying Saturn's rings will prove invaluable when we eventually discover these distant ring systems and attempt to understand their properties and evolution. The search for extrasolar ring systems represents one of the frontiers of modern astronomy, requiring new observational techniques and theoretical frameworks to detect and characterize these distant structures. The knowledge gained from decades of studying Saturn's rings provides the foundation for this effort, offering both the theoretical understanding and observational experience necessary to recognize and interpret ring systems around other worlds. As we look toward the future of ring system research, new missions to Saturn are already being planned that will build upon Cassini's remarkable legacy. These future spacecraft will carry more advanced instruments capable of studying ring dynamics, composition, and evolution in even greater detail than previously possible. Some proposed missions would deploy multiple small spacecraft throughout Saturn's ring system, creating a distributed network of observers that could monitor ring dynamics simultaneously from many different locations. This approach would provide unprecedented insight into how waves propagate through the rings, how temporary structures form and evolve, and how the overall system responds to perturbations from Saturn's moons. Other mission concepts focus on landing spacecraft directly on Saturn's moons to study their compositions, internal structures, and potential for harboring life. These investigations would provide crucial context for understanding the formation and evolution of Saturn's ring system by revealing the properties of the types of objects that may have been disrupted to create the rings. The technological advances that make these ambitious missions possible also open new opportunities for studying Saturn's rings from Earth-based observatories. New telescopes and instruments can resolve features in Saturn's rings that were previously visible only to spacecraft, allowing continuous monitoring of ring dynamics over much longer time periods than any single space mission can provide. This combination of space-based and ground-based observations, supported by increasingly sophisticated theoretical models and numerical simulations, promises to revolutionize our understanding of Saturn's rings over the coming decades. We stand on the threshold of discoveries that may fundamentally change how we think about these magnificent structures and their place in the broader context of planetary system evolution. Yet even as we anticipate these future discoveries, we must remember that Saturn's rings exist in a precious window of cosmic time that will not last forever. The ring-rain process continues to deplete the system, and the gravitational perturbations that maintain its structure are slowly evolving as Saturn's moons migrate to different orbits. The rings that have inspired wonder and scientific investigation for centuries are gradually fading, returning their material to Saturn's atmosphere in a process that began the moment they formed and will continue until the last particle spirals down to the planet's surface. In cosmic terms, this process will be complete in the blink of an eye, a few 100 million years that represent less than 10% of Saturn's total lifetime. This temporal constraint adds urgency to our scientific investigations and poignancy to our aesthetic appreciation of Saturn's rings. We are witnessing a temporary phenomenon, a brief flowering of cosmic beauty that exists only because we happen to live during the precise moment in solar system history when conditions allow such structures to form and persist. The coincidence of our existence with Saturn's ring phase represents one of the most remarkable aspects of our cosmic situation. Of all the billions of years during which intelligent life might have emerged in our solar system, we happen to be here during the relatively brief period when Saturn displays its magnificent crown. This timing connects us intimately to the cosmic processes that created and maintain Saturn's rings, reminding us that we are not separate observers studying a distant phenomenon, but participants in the same cosmic story that gave birth to the rings themselves. The elements in our bodies were forged in stellar cores, just as the ice particles in Saturn's rings condensed from material processed in the hearts of ancient stars. The violence that shattered a moon to create Saturn's rings operates according to the same gravitational laws that hold us to Earth's surface and guide our planet's orbit around the Sun. The electromagnetic forces that create the mysterious spokes in Saturn's rings are manifestations of the same fundamental interactions that power our technology and enable the chemical processes that sustain life. In studying Saturn's rings, we are ultimately studying ourselves and our place in the cosmic order. These magnificent structures remind us that beauty and destruction, order and chaos, permanence and change are all part of the same vast tapestry of existence that connects every atom in the universe to every other atom across space and time. The story of how Saturn got its rings and why it alone among the planets displays such spectacular ring systems is thus not just a tale of planetary science, but a meditation on the nature of existence itself. It reveals the universe as a place where temporary arrangements of matter can create structures of breathtaking beauty and complexity, where the same processes that destroy worlds can also create some of the most magnificent sights in the cosmos. As Saturn continues its stately progression through the solar system, carrying its crown of ice and rock through the cosmic dark, it serves as a reminder that we live in a universe of constant change and transformation. The rings that grace Saturn today are not the same structures that existed when human civilization began, nor will they be the same when our species takes its next great steps into the cosmos. Yet in their temporary existence, Saturn's rings embody something eternal about the universe's capacity for creating beauty, complexity, and wonder from the simplest ingredients and most fundamental forces. They stand as monuments to the creative power of gravity, the organizing influence of resonance, and the delicate balance between order and chaos that characterizes our cosmic home. In the end, Saturn's rings teach us that impermanence and beauty are not contradictory, but intimately connected. The very processes that make the rings temporary also make them magnificent, creating structures of such delicate complexity that they could not exist in any other form or under any other conditions. As we continue to unravel the mysteries of Saturn's rings and search for similar structures around other worlds, we carry with us the knowledge that we are witnessing something truly special. In a universe filled with wonders beyond imagination, Saturn's rings stand out as a reminder that sometimes the most beautiful phenomena are also the most fleeting, existing in brief moments of cosmic time that we are privileged to share. The dance of ice particles around Saturn continues, each orbit bringing subtle changes that slowly but inevitably transform the ring system. New gaps open as gravitational resonances shift, temporary moonlets form and dissolve, and the constant rain of charged particles gradually depletes the system that has captivated human imagination for centuries. This ongoing evolution ensures that Saturn's rings will never be quite the same from one observation to the next, making each glimpse through a telescope or spacecraft image a unique moment in cosmic history. We're not just observing Saturn's rings, but participating in their story, witnessing their gradual transformation as they proceed along the path from catastrophic birth to inevitable dissolution. This transformation process reveals something profound about the nature of time in planetary systems. While human civilizations rise and fall within centuries or millennia, Saturn's rings operate on timescales that dwarf human history, yet remain brief in cosmic terms. The ring particles we observe today have been orbiting Saturn for hundreds of millions of years, each one following its own precise gravitational trajectory while participating in the larger choreography of the ring system. Individual particles within Saturn's rings experience a strange kind of immortality, circling the planet countless billions of times throughout their existence. A single ice fragment the size of a snowball will complete more orbits around Saturn during its lifetime than there are stars visible to the naked eye in our night sky. Yet despite this repetitive motion, each particle's journey is unique, shaped by countless subtle gravitational influences and collisions that gradually alter its path over geological time. The mathematics describing these orbital trajectories are elegant in their complexity, involving equations that account for Saturn's oblate shape, the gravitational perturbations from dozens of moons, and the collective influence of billions of neighboring particles. Each ring particle follows what mathematicians call a quasi-periodic orbit, one that appears regular on short timescales, but exhibits complex, chaotic behavior when viewed over millions of years. This chaotic aspect of ring dynamics helps explain why Saturn's rings maintain their sharp edges and distinct structure, despite the natural tendency of orbital mechanics to spread material outward over time. The same chaotic processes that make individual particle motions unpredictable on long timescales also create a kind of natural mixing that prevents the ring system from settling into a completely uniform distribution. The discovery of chaos in Saturn's rings has connected ring dynamics to one of the most active areas of modern mathematics and physics. Chaos theory, developed initially to understand weather patterns and population dynamics, has found profound applications in celestial mechanics, revealing that even perfectly deterministic systems can exhibit behavior that appears random and unpredictable. This connection between Saturn's rings and chaos theory illustrates how studying planetary systems can illuminate fundamental principles that apply throughout science and mathematics. The same mathematical tools used to understand ring dynamics also help meteorologists predict weather patterns, ecologists model population dynamics, and engineers design stable control systems. The interdisciplinary nature of ring science has attracted researchers from fields ranging from pure mathematics to observational astronomy, creating a vibrant community of scientists who bring diverse perspectives to understanding these magnificent structures. Fluid dynamicists study wave propagation in ring systems, plasma physicists investigate electromagnetic effects, and mathematicians develop new theoretical frameworks for understanding many-body gravitational systems. This collaborative approach has accelerated progress in ring science and revealed connections between seemingly unrelated phenomena. The spiral waves observed in Saturn's rings, for example, are described by the same mathematical equations that govern spiral patterns in galaxies, suggesting deep connections between structures formed on vastly different scales through similar physical processes. The universality of these physical principles means that understanding Saturn's rings provides insights into astrophysical phenomena throughout the universe. The accretion disks around young stars that give birth to planetary systems, the debris disks around mature stars, where planets may be forming or destroying each other, and even the matter spiraling into black holes all operate according to principles that we can study directly in Saturn's ring system. This universality transforms Saturn's rings from a beautiful but isolated phenomenon into a window onto fundamental processes that shape the universe on all scales. Every wave propagating through Saturn's rings teaches us something about how matter behaves in rotating, gravitationally bound systems throughout the cosmos. The precision with which we can measure these phenomena in Saturn's rings provides unprecedented tests of theoretical models that must then be applied to much more distant and difficult to observe systems. When astronomers study the spiral structure of distant galaxies or the accretion disks around black holes, they rely on theoretical frameworks that were developed and tested using observations of Saturn's rings. This connection between local and cosmic phenomena represents one of the most powerful aspects of planetary science. By studying objects within our own solar system in exquisite detail, we develop the tools and understanding necessary to interpret observations of similar phenomena occurring billions of light years away. The Cassini spacecraft's detailed observations of Saturn's rings have thus contributed not only to our understanding of our own solar system, but to our comprehension of astrophysical processes throughout the universe. The mission's legacy extends far beyond planetary science, influencing research in fields ranging from stellar formation to black hole physics. This broader impact of ring research illustrates how fundamental science often produces insights that extend far beyond its original scope. The techniques developed to analyze ring dynamics have found applications in studying everything from traffic flow on highways to the behavior of financial markets, demonstrating the unexpected connections that exist between seemingly unrelated phenomena. The mathematical models used to understand Saturn's rings have become valuable tools for studying any system where large numbers of interacting components give rise to collective behavior. From flocks of birds to swarms of robots, from neural networks in the brain to social networks in human societies, the principles discovered in Saturn's rings provide frameworks for understanding emergence and self-organization in complex systems. This cross-pollination between planetary science and other fields continues to generate new insights and applications. As we develop increasingly sophisticated models of ring dynamics, we simultaneously advance our understanding of complex systems throughout science and technology. The technological innovations required to study Saturn's rings have also produced advances that benefit many other areas of research and engineering. The precision navigation techniques developed for the Cassini mission have improved satellite operations and space exploration capabilities. The image processing algorithms created to analyze ring structure have enhanced medical imaging and remote sensing applications. The radio science techniques used to probe ring structure and particle size distributions have advanced our capabilities for studying planetary atmospheres, measuring gravitational fields, and even detecting gravitational waves from distant cosmic events. Each technological challenge overcome in the study of Saturn's rings has contributed to humanity's broader technological capabilities. These technological spillovers demonstrate how investment in fundamental scientific research generates benefits that extend far beyond the immediate scientific goals. The economic and social returns from planetary exploration missions like Cassini often dwarf their initial costs when all the technological innovations and scientific advances they generate are taken into account. The international collaboration required for missions like Cassini has also strengthened scientific cooperation and cultural exchange between nations. Scientists from dozens of countries work together to design instruments, analyze data, and interpret results from the mission, creating networks of collaboration that continue to produce scientific advances years after the mission's end. These collaborative networks have become models for tackling other global challenges that require international cooperation and interdisciplinary expertise. The same spirit of collaboration that made the Cassini mission successful is now being applied to challenges ranging from climate change to pandemic response, demonstrating how space exploration can strengthen humanity's capacity for working together on shared challenges. The educational impact of Saturn ring research has been equally profound, inspiring countless students to pursue careers in science, technology, engineering, and mathematics. The spectacular images and discoveries from the Cassini mission have captured public imagination and demonstrated the excitement and importance of scientific exploration. Educational programs based on Saturn ring research have reached millions of students worldwide, providing engaging contexts for learning about physics, mathematics, and scientific reasoning. These programs have proven particularly effective at encouraging students from underrepresented groups to pursue scientific careers, helping to diversify and strengthen the scientific workforce. The public engagement generated by Saturn ring research has also strengthened support for scientific research and space exploration more broadly. When people see the beautiful images and remarkable discoveries emerging from missions like Cassini, they gain appreciation for the value of scientific investigation and are more likely to support continued investment in research and exploration. This public support is crucial for maintaining the long-term scientific programs necessary to understand complex phenomena like planetary ring systems. The timescales involved in planetary science research often exceed the typical duration of political administrations or funding cycles, making sustained public support essential for continued progress. The success of the Cassini mission in generating public interest and support has influenced the design of subsequent space missions, with greater emphasis placed on public engagement and education alongside pure scientific investigation. This evolution reflects growing recognition that scientific research thrives when it maintains strong connections to the broader society it serves. The cultural impact of Saturn ring research extends beyond education and public engagement to influence art, literature, and popular culture. The ethereal beauty of Saturn's rings has inspired countless works of art, from realistic astronomical paintings to abstract interpretations of cosmic themes. Writers and filmmakers have drawn inspiration from the discovery that Saturn's rings are temporary features, using this cosmic impermanence as metaphors for human mortality and the fleeting nature of beauty. The rings have become symbols of both magnificence and transience, embodying themes that resonate across cultures and generations. The scientific story of Saturn's rings, with its themes of violent destruction leading to spectacular beauty, has provided rich material for exploring fundamental questions about the nature of existence, the relationship between creation and destruction, and humanity's place in the cosmic order. These themes appear in works ranging from children's books to serious literature, demonstrating the broad cultural resonance of planetary science discoveries. The influence of ring research on popular culture has also helped to shape public perceptions of science and scientists. The collaborative, international nature of ring research has countered stereotypes of science as an isolated, competitive endeavor, instead highlighting the cooperative and creative aspects of scientific investigation. The long-term nature of planetary science research has also provided compelling examples of how scientific understanding develops gradually through the accumulation of observations and insights over many years or decades. This perspective helps the public understand that scientific progress often requires patience and sustained effort rather than dramatic breakthroughs. The interdisciplinary nature of ring research has demonstrated how modern science increasingly requires collaboration across traditional disciplinary boundaries. The study of Saturn's rings involves astronomers, physicists, mathematicians, engineers, and computer scientists working together to tackle problems that no single discipline could solve alone. This collaborative model is becoming increasingly important as scientific challenges grow more complex and interconnected. Climate change, pandemic response, artificial intelligence development, and space exploration all require interdisciplinary approaches that bring together experts from multiple fields. The success of ring research in fostering such collaboration provides a template for addressing other complex challenges facing humanity. The same approaches that have led to breakthroughs in understanding Saturn's rings can be applied to understanding and managing Earth's climate system, developing sustainable energy technologies, or exploring other worlds in our solar system and beyond. The philosophical implications of Saturn ring research continue to generate discussion and reflection among scientists, philosophers, and the general public. The discovery that these magnificent structures are temporary features raises profound questions about the nature of beauty, permanence, and meaning in the universe. Some find the temporary nature of Saturn's rings deeply unsettling, as it suggests that even the most spectacular features of our cosmic environment are ultimately ephemeral. Others find this impermanence beautiful in itself, arguing that the temporary nature of the rings makes them more precious and meaningful rather than less. These philosophical discussions have enriched our understanding of how scientific discoveries influence human culture and values. The study of Saturn's rings has contributed to ongoing conversations about humanity's relationship with nature, the meaning of scientific knowledge, and our responsibilities as conscious observers of the universe. The discovery that we live during the brief cosmic moment when Saturn displays its rings has also sparked discussions about observation, consciousness, and the apparent fine-tuning of the universe for the emergence of intelligent life. While these discussions venture into speculative territory beyond the scope of empirical science, they demonstrate how scientific discoveries can illuminate questions that have puzzled humanity for millennia. The ongoing evolution of Saturn's rings also provides a powerful reminder of the dynamic nature of the universe and the constant change that characterizes all cosmic phenomena. This perspective encourages humility about human timescales and achievements, while simultaneously inspiring awe at our ability to understand processes that operate over geological and cosmic time. As we look toward the future, the study of Saturn's rings continues to evolve and expand in new directions. Advanced computer simulations are revealing previously unknown aspects of ring dynamics, while new observational techniques are providing unprecedented detail about ring structure and composition. The development of artificial intelligence and machine learning techniques is accelerating the analysis of the vast datasets collected by missions like Cassini, revealing patterns and relationships that would have taken human researchers decades to discover using traditional methods. These computational approaches are uncovering new phenomena in Saturn's rings and providing insights into the complex interactions that govern their behavior. Future missions to Saturn are being designed to take advantage of these technological advances, with instruments capable of studying ring dynamics with temporal and spatial resolution far exceeding what was possible during the Cassini era. These missions will answer many current questions about ring formation and evolution, while undoubtedly raising new mysteries that will challenge future generations of scientists. The techniques developed for studying Saturn's rings are also being applied to the search for and characterization of ring systems around exoplanets. As our ability to detect and study planets around other stars continues to improve, we expect to discover ring systems that may be even more spectacular than Saturn's, providing new laboratories for testing our understanding of ring dynamics and formation processes. The comparative study of ring systems throughout the galaxy will provide crucial tests of the theories developed through detailed investigation of Saturn's rings. If these theories are correct, we should find that ring systems around other planets exhibit similar structures and behaviors, modified by the specific conditions around each planetary system. The discovery of diverse ring systems around exoplanets would also provide new perspectives on the apparent uniqueness of Saturn's rings within our own solar system. We might find that spectacular ring systems are actually common around giant planets, and that Saturn's rings are remarkable not for their existence, but for the fortunate timing that allows us to observe them during their most magnificent phase. Alternatively, we might discover that conditions suitable for maintaining spectacular ring systems are indeed rare, making Saturn's rings even more precious as one of the few examples of such structures currently visible in the universe. Either outcome would deepen our appreciation for these magnificent structures and their place in the cosmic order. The search for extrasolar ring systems represents just one frontier in the ongoing exploration of planetary systems throughout the galaxy. As our technological capabilities continue to advance, we can expect to discover phenomena around other planets that are as surprising and beautiful as Saturn's rings, each discovery adding new chapters to our understanding of how planetary systems form and evolve. The legacy of Saturn ring research will thus extend far beyond our own solar system, providing the theoretical frameworks and observational techniques necessary to understand planetary phenomena throughout the universe. The same principles that govern the behavior of ice particles in Saturn's rings will help us interpret observations of debris disks around distant stars, the formation of planetary systems in stellar nurseries, and the complex dynamics of matter in extreme gravitational environments. This universality ensures that the study of Saturn's rings will remain relevant and important as long as humans continue to explore and seek to understand the cosmos around them. The rings themselves may eventually fade and disappear, but the knowledge gained from studying them will continue to illuminate our understanding of the universe for generations to come. In this sense, Saturn's rings have achieved a kind of immortality through human consciousness and scientific understanding. Even after the last ring particle has spiraled down into Saturn's atmosphere, the insights gained from studying these magnificent structures will continue to inform our exploration of the cosmos and our appreciation for the beauty and complexity of the universe we inhabit. The story of Saturn's rings thus becomes part of the larger story of human discovery and understanding, a testament to our species' remarkable ability to observe, question, and comprehend phenomena that operate on scales vastly larger and longer than human experience. Through studying Saturn's rings, we have not only learned about planetary science, but have also discovered something profound about ourselves and our place in the cosmic order. As Saturn continues its journey through space, carrying its crown of ice and rock through the vast darkness between worlds, it serves as a reminder that we live in a universe of constant wonder and discovery. The rings that have captivated human imagination for centuries will continue to evolve and change, offering new mysteries for future generations of scientists to explore and understand. The dance of particles around Saturn continues, each collision and gravitational interaction contributing to the slow but inexorable transformation of these magnificent structures. In their ongoing evolution, Saturn's rings embody the dynamic nature of the universe itself, where nothing remains static. and everything participates in the grand cosmic dance of matter and energy across space and time. And yet, as we've traced this magnificent story of cosmic violence and celestial beauty, we arrive at perhaps the most profound realization of all. Saturn's rings are not merely a collection of orbiting debris, but a living testament to the universe's capacity for transformation. They represent something far more significant than the sum of their countless ice particles. Consider what we've discovered about the fundamental nature of these structures. Every ring particle, from the smallest grain to the largest boulder, exists in a state of constant motion that has persisted for hundreds of millions of years. Each fragment follows its own unique trajectory through space, yet somehow participates in the larger choreography that creates the spectacular patterns we observe. This individual, yet collective behavior reveals something profound about how complex systems organize themselves throughout nature. The same principles that govern the formation of Saturn's ring structure also operate in phenomena as diverse as spiral galaxies, hurricane systems, and even the neural networks that generate consciousness in our own brains. The mathematical elegance underlying this organization suggests that Saturn's rings are not accidents of cosmic history, but inevitable expressions of fundamental physical laws. When matter finds itself in the right conditions, under the influence of the right forces, it naturally organizes itself into structures of breathtaking complexity and beauty. But there's another layer to this story that makes Saturn's rings even more remarkable. The very forces that created their magnificent structure are also slowly but inevitably destroying them. This isn't a flaw in the cosmic design, but rather its most beautiful feature. The rings exist in a delicate balance between creation and destruction, between order and chaos, between permanence and change. This balance creates what scientists call a dissipative structure, a system that maintains its organization by constantly exchanging energy and matter with its environment. Saturn's rings are not static monuments to ancient violence, but dynamic entities that must continuously reinvent themselves to survive. The ring particles we observe today are not the same ones that existed when the rings first formed. Individual fragments are constantly being ground down by collisions, vaporized by impacts, or consumed by Saturn's gravitational appetite. Yet new particles are continuously created through the breakup of larger objects, the condensation of vaporized material, and the capture of debris from Saturn's moons. This constant recycling means that Saturn's rings are simultaneously ancient and young, permanent and temporary, stable and dynamic. They embody the fundamental paradox of existence itself, where nothing remains unchanged, yet everything maintains its essential character through the very process of change. The discovery of this recycling process has revolutionized our understanding of how complex systems maintain themselves over long periods of time. It suggests that persistence in nature doesn't require permanence, but rather the ability to adapt and regenerate in response to changing conditions. This insight has profound implications for understanding many other natural systems. Ecosystems maintain their stability through constant turnover of individual organisms. Civilizations preserve their cultures through the continuous renewal of ideas and institutions. Even our own bodies replace their constituent atoms regularly while maintaining their essential structure and function. Saturn's rings thus serve as a cosmic metaphor for the nature of persistence and identity in a universe of constant change. They remind us that the most enduring features of reality are often those that embrace transformation rather than resist it. The electromagnetic phenomena that create the mysterious spokes in Saturn's rings provide another fascinating window into the dynamic nature of these structures. These ethereal features appear and disappear with a regularity that suggests they're responding to changes in Saturn's magnetosphere, perhaps triggered by seasonal variations in solar radiation or fluctuations in the solar wind. The spokes represent a kind of communication between Saturn's rings and the broader electromagnetic environment of the solar system. They demonstrate that the rings are not isolated from their cosmic context, but intimately connected to processes occurring throughout Saturn's neighborhood and beyond. This connectivity extends to scales both larger and smaller than the ring system itself. The gravitational influences that shape ring structure originate from Saturn's moons, which in turn are influenced by tidal forces from Saturn and perturbations from the Sun and other planets. Meanwhile, the individual collisions between ring particles create acoustic waves that propagate through the ring material, carrying information about local conditions across vast distances. These multiple scales of interaction create what complexity theorists call emergent behavior, where the properties of the whole system cannot be predicted from knowledge of its individual components. Saturn's rings exhibit behaviors that emerge only from the collective interaction of billions of particles, behaviors that would be impossible for any single particle to display alone. The study of these emergent properties has contributed to our understanding of complex systems throughout science and technology. The same mathematical frameworks used to describe ring dynamics have been applied to understanding traffic flow, financial markets, ecological networks, and social organizations. This cross-disciplinary fertilization demonstrates how studying natural phenomena can illuminate principles that operate throughout human society and technology. Saturn's rings have become more than an object of astronomical investigation. They've become a source of insights into the fundamental nature of complexity and organization. The seasonal changes that affect Saturn's rings provide yet another dimension to their dynamic character. As Saturn orbits the Sun over its 29-year cycle, the angle at which sunlight strikes the rings changes dramatically. During equinox periods, when the Sun shines edge-on through the rings, previously invisible vertical structures cast long shadows that reveal the three-dimensional architecture of the ring system. These seasonal variations affect not only what we can observe, but also the physical processes operating within the rings themselves. The changing illumination patterns alter the temperature distribution throughout the ring system, affecting particle behavior and the formation of temporary structures. The electromagnetic environment around Saturn also varies seasonally, influenced by changes in the planet's orientation relative to the solar wind and variations in the intensity of charged particle radiation. These changes trigger different patterns of spoke formation and modify the interactions between ring particles and Saturn's magnetosphere. Understanding these seasonal cycles has required decades of continuous observation, highlighting the importance of long-term monitoring in planetary science. Many phenomena in Saturn's rings operate on timescales much longer than typical spacecraft missions, making ground-based observations and extended space missions crucial for developing comprehensive understanding. The Cassini spacecraft's 13-year mission provided the first opportunity to observe Saturn's rings through nearly half a complete seasonal cycle, revealing variations and behaviors that would have been impossible to detect during shorter missions. This long-duration observation has become a model for future planetary exploration, emphasizing the value of sustained investigation over quick reconnaissance. The data collected during Cassini's extended mission continue to yield new discoveries years after the spacecraft's planned destruction in Saturn's atmosphere. The vast archive of observations provides a resource that will inform ring research for decades to come, demonstrating how investment in comprehensive exploration missions pays dividends far beyond their operational lifetimes. The analysis of this extensive dataset has also driven advances in computational techniques and data processing algorithms. The sheer volume of information collected by Cassini required development of new approaches to data mining, pattern recognition, and automated analysis that have found applications throughout science and technology. Machine learning algorithms developed to identify features in ring images are now being used to analyze medical imaging data, satellite observations of Earth's environment, and astronomical surveys of distant galaxies. The computational challenges posed by ring research have contributed to broader advances in artificial intelligence and data science. These technological spillovers illustrate how fundamental research drives innovation in unexpected directions. The techniques developed to understand Saturn's rings are now helping doctors diagnose diseases, climatologists monitor environmental changes, and astronomers discover new worlds around distant stars. The interdisciplinary nature of ring research has also fostered new collaborations between scientists, engineers, and mathematicians. The complex challenges posed by understanding ring dynamics have required expertise from multiple fields, creating research communities that transcend traditional academic boundaries. These collaborative networks have proven remarkably productive, generating insights that no single discipline could have achieved alone. They've also served as training grounds for a new generation of scientists, comfortable working across disciplinary boundaries, preparing them for the increasingly interdisciplinary challenges facing modern science. The success of these collaborative approaches has influenced the structure of scientific research more broadly, encouraging funding agencies and institutions to support interdisciplinary projects and cross-disciplinary training programs. Saturn's rings have thus contributed not only to our understanding of planetary science, but also to the evolution of scientific practice itself. The educational impact of ring research extends beyond professional scientific training to encompass public education and scientific literacy. The visual appeal and conceptual richness of Saturn's rings make them ideal subjects for engaging students and the general public with scientific concepts and methods. Educational programs based on ring research have proven particularly effective at illustrating the nature of scientific inquiry, showing how observations lead to hypotheses, which generate predictions that can be tested through further observations or experiments. The iterative process of scientific understanding is beautifully exemplified in the centuries-long investigation of Saturn's rings. The historical development of ring science also provides compelling examples of how technological advances drive scientific progress. Each improvement in telescope design or spacecraft capability has revealed new phenomena and raised new questions about ring structure and behavior. This technological progression continues today, with new instruments and analysis techniques constantly expanding our ability to study ring dynamics. Future missions to Saturn will carry instruments capable of measurements that would have seemed impossible during the Cassini era, promising discoveries that may revolutionize our understanding once again. The ongoing technological evolution ensures that Saturn's rings will continue to surprise us with new phenomena and unexpected behaviors. Each generation of scientists brings new tools and perspectives to their investigation, uncovering layers of complexity that previous generations could not have imagined. This perpetual potential for discovery keeps ring research vibrant and exciting, attracting young scientists who see opportunities to make fundamental contributions to our understanding. The combination of spectacular beauty, deep scientific mystery, and technological challenge makes Saturn's rings an ideal focus for ambitious research careers. The global nature of ring research has also contributed to international scientific cooperation and cultural exchange. Scientists from dozens of countries have participated in ring studies, sharing data, techniques, and insights across national and cultural boundaries. This international collaboration has strengthened scientific relationships and demonstrated how shared curiosity about natural phenomena can transcend political and cultural differences. The study of Saturn's rings has contributed to building the global scientific community that increasingly characterizes modern research. The peaceful, cooperative nature of planetary exploration has also provided a model for international relations more broadly. When nations work together to explore other worlds, they demonstrate humanity's capacity for cooperation and shared purpose in addressing challenges that transcend national boundaries. The success of international cooperation in space exploration has influenced approaches to other global challenges, from climate change to pandemic response. The collaborative frameworks developed for planetary missions provide templates for addressing problems that require coordinated international action. Saturn's rings have thus contributed not only to scientific knowledge, but also to human cooperation and understanding. They remind us that some of the most profound questions about existence transcend the boundaries that often divide us, inspiring collaboration and shared wonder at the magnificent universe we inhabit. As we stand at the threshold of new discoveries about Saturn's rings and similar structures throughout the universe, we carry with us the accumulated wisdom of centuries of investigation. Each generation of scientists has built upon the work of their predecessors, creating an intellectual legacy that continues to grow and evolve. The story of Saturn's rings is ultimately a story about human curiosity and ingenuity, about our species' remarkable ability to observe, question, and understand phenomena that operate on scales vastly beyond our everyday experience. Through patient observation and careful analysis, we have decoded the history written in the motion of countless ice particles orbiting a distant world. This achievement represents one of the great triumphs of human intellect, demonstrating our capacity to comprehend processes that unfold over millions of years and involve forces operating across hundreds of thousands of kilometers. The rings that once seemed like divine ornaments adorning a celestial sphere are now understood as natural phenomena, governed by physical laws we can describe with mathematical precision. Yet this scientific understanding has not diminished the wonder and beauty of Saturn's rings, but rather enhanced it. Knowing how the rings formed and how they maintain their structure makes them more remarkable, not less. Understanding their temporary nature makes their current magnificence more precious, not less significant. The marriage of scientific knowledge and aesthetic appreciation that characterizes our relationship with Saturn's rings exemplifies the highest aspirations of human culture. When we can simultaneously understand and marvel at natural phenomena, we achieve a kind of comprehension that transcends purely rational analysis. This integrated understanding represents perhaps the greatest gift that Saturn's rings offer to human consciousness. They remind us that we are capable of both rigorous scientific investigation and profound aesthetic experience, that knowledge and wonder can coexist and mutually enrich each other. As Saturn continues its ancient journey through the solar system, its rings slowly evolving and changing with each passing moment, these magnificent structures serve as both scientific laboratory and cosmic artwork. They embody the universe's capacity for creating beauty through purely natural processes, while simultaneously providing insights into fundamental physical principles that operate throughout the cosmos. The continuing story of Saturn's rings unfolds on timescales that dwarf human civilization. Yet we have been privileged to witness a crucial chapter in their evolution. Through our observations and investigations, we have become part of their story, conscious observers who have decoded their history and glimpsed their future. In studying Saturn's rings, we have discovered not only the mechanisms that created and maintain these magnificent structures, but also something profound about our own nature as conscious beings capable of wonder and understanding. The rings serve as a mirror, reflecting both the universe's creative power and humanity's intellectual achievements. The legacy of Saturn ring research will endure long after the rings themselves have faded, preserved in the scientific knowledge, technological innovations, and cultural inspirations they have generated. Through human consciousness and scientific understanding, these temporary structures have achieved a kind of permanence that transcends their physical existence. The dance of particles around Saturn continues, each orbit adding another moment to a story that began with violence and destruction, but created one of the most beautiful sights in our solar system. In their graceful motion through the cosmic dark, Saturn's rings embody the universe's endless capacity for transformation, reminding us that even the most catastrophic events can give birth to structures of transcendent beauty and meaning. As we drift deeper into this cosmic meditation, let us pause to consider something that challenges everything we thought we knew about planetary formation. Recent discoveries have revealed that Saturn's ring system may not be the product of a single catastrophic event, but rather the result of multiple episodes of destruction and renewal spanning hundreds of millions of years. This revelation emerges from detailed analysis of the ring's composition and structure, which shows subtle variations that suggest different formation episodes. Some regions of the rings contain ice particles that appear older and more weathered, while others display the pristine characteristics of recently formed material. This patchwork of ages tells a story far more complex than simple disruption of a single moon. Imagine Saturn's neighborhood as it existed hundreds of millions of years ago, populated by a family of moons that no longer exist. One by one, these worlds met their fate in Saturn's gravitational embrace, each contributing its remains to the growing ring system. The first moon to be destroyed might have created a sparse, narrow ring system. Later disruptions added material and complexity, building the magnificent structure we observe today. This multi-episode formation scenario helps explain some of the puzzling features that have long mystified ring scientists. The remarkable purity of the ring material, composed almost entirely of water ice with very little rocky contamination, suggests that the destroyed moons had already been processed by Saturn's tidal forces for millions of years before their final destruction. Tidal heating from Saturn's gravity would have gradually separated the lighter, ice-rich materials from denser rocky components within these doomed moons. By the time they crossed the Roche limit and were torn apart, they had been transformed into essentially pure ice worlds, creating the brilliant, highly reflective ring system we admire today. The timing of these destruction events appears to have been influenced by the slow migration of Saturn's moons due to tidal interactions with the planet. As moons gradually spiral inward or outward from their original orbits, some cross critical thresholds, where gravitational resonances with other satellites destabilize their paths, sending them on collision courses with Saturn or into crossing orbits where mutual encounters become inevitable. This migration process continues today, ensuring that Saturn's ring system remains dynamically active. Current observations suggest that some of Saturn's smaller moons may be on trajectories that will lead to their eventual destruction and incorporation into the ring system. The rings we see today may be just the latest chapter in a story of continuous creation and destruction that has persisted throughout Saturn's history. The realization that ring formation is an ongoing process, rather than a single ancient event, has profound implications for understanding similar systems around other planets. It suggests that spectacular ring systems may be more common than previously thought, existing whenever the right combination of planetary mass, moon population, and orbital dynamics creates conditions for sustained ring maintenance. This dynamic view of ring evolution also explains why Saturn's rings appear so young compared to the planet itself. Rather than being ancient structures that have somehow survived for billions of years, they represent the current state of a system that has been continuously renewed through the destruction and reformation of ring material over geological time. The gravitational choreography that orchestrates this ongoing renewal involves not just Saturn and its rings, but the entire system of moons that surround the planet. Each satellite contributes to the complex web of gravitational influences that determine which objects survive, which are destroyed, and how their remains are distributed throughout the ring system. The largest moons, like Titan and Iapetus, orbit far enough from Saturn to remain stable for billions of years, but their gravitational influence helps shape the overall architecture of the system. Intermediate-sized moons like Enceladus and Mimas occupy more precarious positions, where their long-term survival depends on delicate orbital relationships that could be disrupted by relatively small perturbations. The smallest moons and moonlets exist in the most dynamic environment of all, with lifetimes that may be measured in millions rather than billions of years. These tiny worlds are the most likely candidates for future ring-forming events, their destruction contributing to the ongoing renewal of Saturn's magnificent crown. The discovery that Saturn's rings are actively maintained through ongoing destruction processes has transformed our understanding of what it means for a planetary system to be stable. Rather than requiring static equilibrium, long-term stability may actually depend on dynamic processes that continuously reshape and renew system components. This insight has implications for understanding planetary system evolution throughout the universe. It suggests that what we observe around any given planet at any given time may represent just a snapshot of a continuously evolving system, where current configurations result from millions of years of ongoing gravitational interactions. The apparent youth of Saturn's rings, rather than being a puzzling anomaly, may thus be a natural consequence of their dynamic nature. Ring systems may typically exist in states of continuous renewal, with their apparent ages reflecting the timescales of the processes that maintain them rather than the time elapsed since their initial formation. This perspective suggests that ring systems around other planets may be more common than we currently realize, existing in various stages of development and decay depending on the specific conditions around each world. Some planets may currently lack visible rings, not because they never had them, but because they happen to be in quiet phases between ring-forming events. The search for ring systems around exoplanets takes on new significance in light of this dynamic view of ring evolution. Rather than looking only for permanent stable structures, we should also be alert for the signatures of recently formed or rapidly evolving ring systems that may represent planets caught in the act of ring creation or destruction. The temporal nature of ring systems also means that their detection around exoplanets may require monitoring over extended periods to catch systems during their most spectacular phases. A planet that appears ringless in one observation might display magnificent ring structures when observed years or decades later, if it experiences a ring-forming event during the intervening period. This variability adds both challenges and opportunities to the search for extrasolar ring systems. While it makes rings harder to detect through single observations, It also means that continued monitoring of known planetary systems may reveal ring formation events as they occur, providing unprecedented opportunities to study these processes in real time. The dynamic nature of Saturn's rings also influences how we think about their ultimate fate. Rather than simply fading away as ring rain depletes the system, the rings may undergo periodic episodes of renewal that could extend their lifetime far beyond current estimates based on steady depletion rates. If Saturn continues to experience moon-destroying events every few 100 million years, the ring system could persist for billions of years into the future, with each renewal episode creating new structures and resetting the depletion clock. The magnificent rings that have inspired human observers for centuries might thus represent not a fleeting phenomenon, but a permanent feature of Saturn's identity. This possibility transforms our perspective on the cosmic timing that allows us to observe Saturn's rings. Rather than being extraordinarily fortunate to exist during the brief period when Saturn displays rings, we may be witnessing a feature that has persisted throughout most of Saturn's history and will continue long after our civilization has passed into cosmic memory. The question then becomes not whether Saturn's rings will survive, but how they will evolve. Future ring-forming events will undoubtedly create new structures and modify existing ones, ensuring that Saturn's rings continue to surprise and delight observers for eons to come. The gravitational interactions that drive ring evolution operate according to mathematical principles that reveal deep connections between seemingly unrelated phenomena throughout the universe. The same equations that describe the spiral waves propagating through Saturn's rings also govern the formation of spiral arms in galaxies, the behavior of sound waves in fluids, and the propagation of quantum mechanical wave functions. These mathematical universals suggest that Saturn's rings are not merely beautiful accidents, but inevitable expressions of fundamental physical laws. When matter finds itself in the right conditions under the influence of appropriate forces, it naturally organizes itself into structures that exhibit similar mathematical properties regardless of the scale on which they operate. The study of these universal patterns has contributed to our understanding of emergence and self-organization throughout nature. Saturn's rings provide a particularly clear example of how simple physical laws can give rise to complex, organized structures that exhibit behaviors far richer than might be expected from their basic components. This principle of emergence operates at every level of ring structure, from the microscopic interactions between individual particles to the large-scale patterns that span the entire ring system. Local interactions between neighboring particles create regional structures, which in turn participate in system-wide behaviors that influence the evolution of the rings as a whole. The hierarchical nature of these interactions creates what complexity scientists call scale-free phenomena, where similar patterns and behaviors appear at different scales throughout the system. The spiral waves that organize ring material on scales of thousands of kilometers emerge from particle interactions occurring over distances of meters, demonstrating how local processes can generate global structures. This multi-scale organization makes Saturn's rings valuable laboratories for studying emergence and self-organization in complex systems. The principles discovered through ring research have applications to understanding phenomena ranging from the formation of planetary systems to the behavior of neural networks in biological brains. The mathematical tools developed to analyze ring dynamics have found applications in fields as diverse as fluid mechanics, plasma physics, and even economics. The same techniques used to understand how density waves propagate through Saturn's rings help engineers design more efficient turbines and economists model the flow of information through financial markets. This cross-pollination between planetary science and other disciplines continues to generate new insights and applications. as our understanding of ring dynamics becomes more sophisticated, it opens new possibilities for applying these insights to technological challenges and fundamental scientific questions. The ongoing evolution of computational techniques also promises to revolutionize our ability to study ring dynamics. Advances in artificial intelligence and machine learning are enabling new approaches to analyzing the vast datasets collected by spacecraft missions, revealing patterns and relationships that would have taken human researchers decades to discover. These computational advances are particularly important for understanding the long-term evolution of ring systems, which involves processes operating over timescales much longer than human observation periods. Computer simulations can now model ring evolution over millions of years, providing insights into processes that cannot be directly observed. The results of these simulations often reveal unexpected behaviors and evolutionary pathways that challenge our intuitive understanding of how ring systems develop. They show that ring evolution is far more complex and unpredictable than simple models suggest, with small changes in initial conditions sometimes leading to dramatically different outcomes. This sensitivity to initial conditions is another manifestation of the chaotic dynamics that characterize ring systems. While the overall evolution of the rings is determined by well-understood physical laws, the specific details of how structures form and evolve depend on countless small perturbations that accumulate over time. The chaotic nature of ring evolution means that while we can understand the general principles that govern ring behavior, predicting the exact future state of the ring system may be fundamentally impossible. This limitation is not a failure of our scientific understanding, but a consequence of the intrinsic unpredictability that characterizes many natural systems. The presence of chaos in ring dynamics connects Saturn's rings to one of the most active areas of modern science and mathematics. Chaos theory has revealed that unpredictable behavior is not a sign of random or mysterious forces, but a natural consequence of nonlinear interactions in deterministic systems. The discovery of chaos in Saturn's rings has helped scientists understand why these systems maintain their complex structure, despite the natural tendency of orbital mechanics to smooth out irregularities over time. Chaotic dynamics continuously generate new structures and patterns, ensuring that the rings never settle into a completely uniform static state. This dynamic balance between order and chaos is what keeps Saturn's rings perpetually interesting and beautiful. The same forces that create the elegant spiral patterns and sharp divisions also introduce the irregularities and asymmetries that prevent the rings from becoming boringly perfect. The interplay between order and chaos in Saturn's rings reflects a fundamental characteristic of complex systems throughout nature. From the weather patterns in planetary atmospheres to the firing patterns of neurons in brains, many natural phenomena exhibit this same balance between predictable structure and unpredictable variation. Understanding this balance has practical implications for many technological applications. Engineers designing control systems for spacecraft, aircraft, and other complex machines must account for the chaotic behaviors that can emerge from seemingly simple interactions between system components. The lessons learned from studying chaos in Saturn's rings have contributed to advances in control theory, helping engineers design systems that remain stable and predictable even when operating in complex nonlinear regimes. These advances have applications ranging from autonomous vehicle navigation to the management of electrical power grids. The philosophical implications of chaos in natural systems continue to generate discussion among scientists, mathematicians, and philosophers. The discovery that simple deterministic laws can produce unpredictable behavior challenges traditional notions about causality and predictability in natural phenomena. Some interpret the presence of chaos as evidence for fundamental limits to human knowledge and prediction, while others see it as opening new possibilities for understanding the creative aspects of natural processes. The ongoing debate reflects the profound implications that chaos theory has for how we understand the relationship between scientific knowledge and natural phenomena. Saturn's rings, as one of the most accessible examples of chaotic dynamics in action, continue to inform these discussions and provide concrete examples of how chaos manifests in real physical systems. Their beauty and complexity serve as reminders that the most profound truths about nature often emerge from the interplay between order and unpredictability. The study of Saturn's rings has thus evolved from a purely descriptive endeavor focused on cataloging their features to a comprehensive investigation of fundamental principles that operate throughout the natural world. The rings have become a window onto processes that shape everything from the formation of planetary systems to the evolution of life itself. This transformation reflects the broader evolution of science, from a collection of separate disciplines studying isolated phenomena to an integrated enterprise that recognizes the deep connections between seemingly unrelated aspects of the natural world. Saturn's rings exemplify how studying any natural phenomenon in sufficient depth eventually leads to insights that illuminate the fundamental unity underlying all natural processes. The continuing investigation of Saturn's rings promises to yield further insights into these fundamental principles, as our observational capabilities and theoretical understanding continue to advance. Each new discovery adds another piece to the vast puzzle of how the universe organizes itself into the complex, beautiful structures we observe throughout nature. The rings that have captivated human imagination for centuries will undoubtedly continue to surprise us with new phenomena and unexpected behaviors as we develop more sophisticated ways of studying them. Their story is far from complete, with new chapters being written each day as the rings continue their ancient dance around Saturn. In their ongoing evolution, Saturn's rings embody the dynamic nature of the universe itself, where nothing remains static and everything participates in the grand cosmic process of continuous creation and transformation. They remind us that we are witnessing not just a beautiful astronomical phenomenon, but a manifestation of the creative forces that shape all of existence. The dance continues, particles streaming through space in patterns of breathtaking complexity and beauty, each orbit adding another moment to a story that connects the smallest interactions between ice crystals to the grandest processes that govern the evolution of planetary systems throughout the cosmos. In Saturn's rings, we glimpse both the intimacy and immensity of the universe we call home. Tonight, as we reach the end of our cosmic journey through the rings of Saturn, we find ourselves changed by what we've witnessed. We began with a simple question about why Saturn alone wears this magnificent crown, and we've discovered a story far more profound than we could have imagined. We've seen how catastrophic violence can birth transcendent beauty, how the destruction of entire worlds creates some of the most spectacular sights in our solar system. We've learned that Saturn's rings are not ancient monuments but young, dynamic structures that exist in our precise moment of cosmic history through a combination of perfect conditions and extraordinary timing. The rings teach us that the universe operates on principles both elegant and chaotic, where gravitational resonances create spiral waves that mirror the mathematics of distant galaxies, where individual particles follow simple laws yet collectively produce behaviors of stunning complexity. They remind us that we are witnessing something truly precious, a fleeting cosmic performance that will eventually fade, but whose beauty has been captured forever in human consciousness. As you drift toward sleep tonight, carry with you the knowledge that above your head, billions of ice particles continue their eternal dance around a distant world, each one following its own precise trajectory while participating in a symphony of motion that spans hundreds of thousands of kilometers. In their graceful orbits, they embody the universe's endless capacity for creating wonder from chaos, beauty from destruction, and meaning from the simplest physical laws. Sweet dreams, fellow travelers in this magnificent cosmos. I wish you a very good night. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers.